Hey YouTube, in this video we're going to confront what we call binomial expansion. That is to say, we've been talking about adding, subtracting, and multiplying polynomials. What if we had a binomial like a plus b and we raised it to a power? We would get some resulting polynomial that would depend upon, how long it is, would depend upon what power we were raising it to. The higher the power we're raising it to, well then the longer it would be, this expression. But this is what we're going to refer to as binomial expansion. And the thing is, in math, we like to talk and focus on patterns all the time, talk about and focus on a pattern. So what we see when we expand this binomial a plus b to the n, where n, starts at 0 and gets bigger and bigger and bigger, is this pattern that shows up here. And I just want to kind of take you through it. We say, well, if n is our power and a plus b is our binomial and we're raising it to the nth power, first thing we'll say is this: what if n equals 0? And if n equals 0, and I want to show you this on any calculator, so I'll wait a second here for this calculator to open, but anything to 0 power is just 1 all of the time. So if I said 4 to the power of 0, the calculator says, dear person, it is 1. Okay, the only thing we don't raise to the 0 is 0 itself. Let's see what this says here. Ooh, that's crazy, because I would tell you that that's in determinant form. But by the way, we're just going to say that this binomial to the 0th power would be just 1. If we raise this a plus b to the first, well, obviously we would get itself, but I would get 1a plus 1b, and these are both to the first power here. The moment we square this, now we did actually square this in the last video. We said a plus b squared, this thing right here. We got a squared plus 2ab plus b squared, which I want you to see as this expression that you see here. But we get 1a squared plus 2ab plus 1b squared. And then last but not least, if we were to actually cube a plus b to the 3rd power, cube all that out, you actually get this resulting expression right here, which is 1a cubed plus 3a squared b plus 3a to the first b squared plus 1b cubed. Now, a plus b to the 4th and the 5th. These are these expressions you see here. And yes, somebody took their time to do them for you, so congratulations. But what, again, we're looking for here are patterns. So what you'll see is that all of these blue numbers here, these are what we refer to as the coefficients of the terms in our expansion. And that's important because, when we look at these right here, I look at the variables. Let's just start by looking at the variables here. When I took a plus b to the first, I get a to the first, b to the first. When I took a plus b to the second, I get a squared plus a to the first, b to the first, plus b squared. When we take a plus b to the 3rd, we start with a having all of that 3 right there, all of the n. And then as we go to the right, look what happens. A becomes to the 2nd power, b becomes to the 1st power in the next term. Then it becomes a is the 1st power, b is the 2nd power. And then it becomes a is the 0th power, which doesn't exist there, and we'd say b is to the 3rd. So this n value out in front right here basically tells us that if you took a plus b, even if I took a plus b to the 6th power, what I would get is this: a to the 6th plus a to the 1 less b to the 1 more plus a to the 4th b to the 2nd plus a to the 3rd b to the 3rd plus a to the 2nd b to the 4th plus a to the 1st b to the 5th plus b to the 6th. And you notice that in each instance, these exponents that you see here, 6, 5 and 1, 4 and 2, 3 and 3, they all add up to the value of n that you have out front. In this case, we had 6 right there. So the only thing that's missing from this expression right here are the coefficients. And so the coefficients are told to us using this nifty little thing called Pascal's triangle. And Pascal's triangle, the way it works is this. We say that it has 1s on the outside diagonal. So in Pascal's triangle, the first and last numbers on each row are 1. We say every number other than 1 is the sum of the closest 2 numbers in the row directly above it. So in terms of how we're getting these coefficients here, we'd say, well, this 2 is just the result of adding this 1 and this 1. That 3 right there is the result of adding the 1 and the 2 that were closest to it in the row before. So really these things, they kind of like trickle down into the next term there. So if I had to fill in the next row of Pascal's, I would say, well, first of all, this would be a 1 and this would be a 1 to begin and end the row. And I say 1 plus 5 is 6. 5 plus 10 is 15. 10 plus 10 is 20. 10 plus 5 is 15, and then 5 plus 1 is 6. So you can see that there is symmetry on the left and right side of this triangle. But also that we just get the next row by adding the 2 entries right above this number to get it. Okay. So in terms of what Pascal's triangle does for us, well, I can always go and recreate this triangle, but it tells us, depending upon the n that we're raising our binomial to the power of, this power of n, what our coefficients should be on our expansion. Okay. So One really quick thing I want to point out here is this, that the first row, when we split Pascal's triangle up, when you create your own Pascal's triangle on your paper, the first row is considered to be the 0th row. The 0th row is considered to be this first row right here. The second row here is going with the first n here. So if n is to the first power, you use the second row, and so on and so forth. So it's kind of like our row values here are a number behind the actual row that you're in, kind of thing. Okay, so let's take a look at this. I have a set of instructions down here, but I think it's useful to just run through an example here. Looks like we have a binomial here to the nth power. So the first thing I'm going to recognize are a, b, and n. And so n is this power that we're raising this to. We say to the nth power, and then our a and b are our first and second parts of this binomial respectively. So it seems to me that our first part here is the x, and the second part here is the 3. So what I end up with here, and actually one thing I want to do before we do this is change this to a sum. Okay, so this is important to note. If you have a difference in here, we're going to change this over to being a sum, because this binomial expansion only works, you look at each of these examples that we raised a plus b to the power of something, is with b being positive. So if it's ever negative, we'll rewrite it as add the opposite. And what that's going to do is it's going to change our b value here to being a -3. But that being said, because I'm raising this to the 4th, here's what I essentially want you to see. And I'm going to kind of trap these off here. Our n being 4 means that we're going to start by taking our a value here to the 4th. So we have our a value to the 4th, plus now blank, and what I'm going to do is I'm going to write 3 and 1. Plus our coefficient times now this, and I'm going to have to go off my page here, plus squared and squared, plus coefficient, first power and third power, oops, see I'm already thinking 3, plus, now I'm going to bring this down over here, sorry, coefficient to the 4th. So what this looks like is like this. We have our a here, we have a, b, a, b, a, b, b. And so what we're going to do is we're just going to go put these in for our a values and our b values respectively, and then we're going to go back and assess the situation and say what should our coefficients be. So in this case, all of these a fields in the front here should be filled in with this x that we see here. So we have an x, 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 and then all of our b fields get filled in with this -3 value, -3, -3, -3, -3. So you'll notice on the first term here we have a to the 4th, or our first thing to the 4th. There is no b term there. And on the last term here, we have our b term being taken to the 4th, but the a term, it is no longer being raised to a power. So this is our expansion right here. The only thing we need to do is go back and find the coefficients. So because this is the 4th row, and I know I have this right over here, I can just go back over here and I can look and say, okay, so which one of these rows corresponds with the 4th row? I'll put those coefficients in. So I have 1, 4, 6, 4, and 1. And I want you to notice that there were just as many coefficients as what we needed to fill in this expansion. So to simplify this, I'd say 1x to the 4th. Well, x to the 4th is x to the 4th, so I just get x to the 4th from this term. Now I have 4x cubed -3 to the 1st. Now -3 to the 1st gives me -3, and -3 times a 4 is going to give us a -12 here, and then we have x to the 3rd. So now this next term, I'm going to start by doing my exponents here. Looks like I would take -3 and square it, so it gives me a 9, and 9 times 6 is 54. So I have 54, looks like x squared. And then I have over here, I have 4 times -3 cubed. Now -3 cubed is -27. And -27 times is 4. Let's see here. -80, -108. Sorry for the mental math. You can check on a calculator. But I also have this x to the 1st term right here. So I have x to the 1st. And then last but not least, -3 to the 4th. That'd be like 9 times 9 is 81. So this would be our binomial expansion. And I want you to understand that had you done this the long way, you would have had to have taken x minus 3 times x minus 3 times x minus 3 times x minus 3, and then do this 2 things at a time, get that answer, take that times this next one here, get that answer, take that times this next one here. It is a lot easier to just expand it using binomial expansion. So a little bit quicker on this one. I'm going to identify what's our a part, what's our b part, and what's our n. So we have our a part is 2y, our b part is a positive 4, and our n part is 3. So because we're cubing this, our expansion would start with this. We'd say a cubed, something a cubed plus, now our a squared b to the 1st term is next. We say plus our coefficient of our a to the 1st, b to the 2nd term, plus our coefficient of our b to the 3rd term. And so we're going to go put in now a, we have a, b, a, b, b. We're going to go put all these in. So we say our a here is 2y. So we say 2y, 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 2y. And then our b term here is 4, 4, and 4. So now we just need our coefficients. And so because it's the third row of Pascal's, maybe I'll make my own triangle. 1, 1, 1, 1, 2, 1. And then we would say this is 0th row, first row, second row. We need the next row. So it'd be 1, 3, 3, and 1. So 1, 3, 3, and 1 are the values of the coefficients right here. So I'll tell you what, this is actually the expansion right here. This is what this all equals. We just need to clean it up. So I would say 1 times 2y to the third power. 2y to the third power, that would be 2y times 2y times 2y. We would get 8y cubed. Here we would get 3. Now I'm going to take my time on this one. 3 times 2y squared would be 3 times 4y squared times that 4 that you see right there. Plus 3 times 2y times 16. And then plus 4 to the third power, which 4 to the third power is 64. So now we'll go back and rewrite this one more time. Hopefully this is the last time. 8y cubed. Now 3 times 4 is 12. 12 times 4 is 48. So I have 48 y's squared. Now 3 times 2 is 6. 6 times 16 here would be 96. So again, sorry for the mental math. We say plus 64. But this would be the cube of that binomial in a really quick fashion without having to FOIL everything out. Cheers.